Hi everyone, my name is Arun Iyer. I'm a principal researcher from Microsoft Research Lab India. Today, I'm going to talk about challenges in multi-tenant graph representation learning for recommendation problems. To give a brief overview of the talk, I'll be first talking about graph representation learning in Office, particularly about our project Digo. I'll briefly talk about the graphs that are available to us and what Project Digo aims to achieve by learning representations on these graphs. Then I will talk about the various challenges involved. Scalability is a perennial challenge and is well understood, so I won't be covering that in this talk. I'll talk mostly about other challenges that have not received enough attention in literature. We have answers to few of these challenges, but several are yet to be overcome. Uh, Before talking about graph representation learning in Office, let us talk about the graph that is available to us. We have a rich interaction graph available in Office. A user 1 sends email E to user 2. A user 1 shares document D with user 2. A user 1 sends Teams message M to user 2. All of these interactions give a rich graph in Office. Office also has plethora of recommendation problems, like recommending relevant emails to meetings, relevant documents to meetings, etc. In light of this, we started the project DIGO, which stands for Deep Entity Embeddings from Graphs in Office. In this project, our goal is to learn embeddings from the rich interaction graph and utilize them in downstream recommendation problems and see if the recommendation tasks benefit from them. We also aim to address the practical challenges involved in building such a system. We expect the embeddings to be learned and used in two modes. Mode 1. We pre-learn the embeddings from the graphs, and then the embeddings are used by the downstream recommendation models directly. Mode 2. We provide modules which can do supervised or semi-supervised embedding learning, and these modules are used by the downstream tasks to generate task-specific embeddings. Due to the computational overhead involved in learning the embeddings, we expect mode 1 to be the most popular mode, but some applications may choose mode 2. To reiterate, mode 1, we pre-learn the embeddings from the graphs, and then the embeddings are used by the downstream recommendation models directly. We have done experiments with embeddings in mode 1 settings for several recommendation scenarios. All the scenarios show significant improvement in performance over production baselines. It shows that the embeddings learned from these interaction graphs are valuable for several recommendation tasks. However, there is still a lot of work left to build a complete practical system. In the next few slides, I will outline some of the challenges we need to overcome to build this practical system. The first challenge we need to overcome is how do we learn embeddings for fast-moving entities? Graphs in Office have entities which are slow-moving and fast-moving. Slow and fast are defined with respect to their relevance to users over time. For example, people, teams, channel, which are relevant to a particular user, do not change rapidly over time. Thus, they are classified as slow-moving entities. On the other hand, relevance of other entities like emails, documents, etc., change rapidly over time. For example, a document may have a transient relevance. Example, all document related to the summit may be relevant only during the summit. Or some documents will have seasonal relevance. For example, hiring guideline document will be relevant during hiring seasons. And there are some long-term relevant documents. For example, software architecture documents are likely to be relevant for a longer period of time. Also, these entities are added to the graph at a much faster rate. Thus, such entities are classified as fast-moving entities. Learning embeddings for all the fast-moving entities will be computationally expensive, and it is unclear how much benefit it will entail. To address this problem, we propose to derive the embeddings for the fast-moving entities by aggregating slow-moving entities that interact with them. For example, we can derive email embeddings based on users who participate in that email. Towards that, we propose the heterogeneous graph convolutional model, HEAT-GCN. We showed improvements on various recommendation data sets. Additionally, our experiments with real-world recommendation problems in Office showed promising improvements over production baseline models. While we have a working solution for this particular challenge, the next few challenges are all reasonably unsolved. The next challenge we want to look at is robustness against label graph correlation. For node classification, impact of label graph correlations on performance of GNNs is understood reasonably well. Several metrics have been proposed that characterize the performance of GNNs. However, We believe that there is still significant gap in our understanding in this space. For example, in our KDD workshop paper, we showed that the concatenation of truncated SVD of node features and graph gave significant improvement over SOTA models. Rather than answering a particular question, we wrote this paper to raise several questions in this space. On the recommendation side, we don't yet know whether similar label graph correlation metrics exist and whether they have any impact on the recommendation task. And if they do have an impact, then what models will mitigate those issues? These are the open questions that need to be answered. We are currently in the process of understanding this problem in the classification setting and then slowly bring our learning to the recommendation problems. The next challenge I would like to talk about is user privacy controls and how we make sure that the embeddings respect them. User privacy is of utmost importance to Microsoft. Today, any application that wishes to use these graph embeddings has to go through a strict privacy process. During the process, several privacy concerns with the applications will be raised, and the application owners are forced to offer solutions to these privacy concerns before moving ahead with the usage of embeddings. However, we would like to go beyond this. For example, can we provide some privacy controls which are easy to use with low cognitive load directly to the users? Can we incorporate the decisions generated through these privacy controls in the embedding learning algorithm so that our embeddings respect the privacy that the user desires to have? There are some works that have started to look in this direction. For example, the highlighted paper talks about preserving link privacy, but talks about it at the global level. Globally preserving privacy will run counter to our requirements in recommendation tasks. With user privacy controls, we can get more fine-grained privacy requirements. For example, we may have explicit knowledge of the links whose privacy we need to preserve. Thus, we believe that incorporating such knowledge in embedding learning algorithms will be very useful. The next challenge I want to talk about is consistency of embeddings for downstream tasks. In Project Digo, we currently plan to learn embeddings at a certain cadence, say every month. Let us say we construct graph GT at time t and learn embeddings on it, call it ET. Now at time t plus 1, we construct graph GT plus 1, and we can learn embeddings from that graph, call it ET plus 1. While this in itself is not a problem, but there are implications for the downstream task. Every time we learn a new set of embeddings, the downstream model has to be retrained. There are some things we need to understand about the deployment process for a downstream model. A downstream model first goes through an internal team bug bashing, where the development team checks the model performance on their own data to find any obvious problems with the model. Then the model is sent through several A/B testing rounds. All the results from A/B testing rounds are compiled, and then a final decision is made whether to ship the model into production or not. All this process can easily take anywhere from 1.5 to 2 months. Since there is significant cost associated with deployment of models, an application owner would be unwilling to train a new model every month. So this raises several questions for us to address. How do we learn embeddings at time t plus 1, that is ET plus 1, such that the model trained with ET does not regress significantly? Under what conditions is this possible? How can we measure the sensitivity of the downstream tasks and take that into account while learning the embeddings? And these are all open questions that we don't have an answer to at the moment. The final challenge that I would like to talk about is impact of tenant overlap on downstream tasks. There are several different tenants in Office. Each tenant graph is treated as independent graph and embeddings are learned independently. Thereby, embeddings of each tenant can overlap with one another. However, downstream applications often learn one model across all tenants. In such a scenario, can overlap of embeddings cause problems in training of models for downstream applications? For example, consider the problem of recommending Teams channels to user. In tenant 1, Teams channel 1 T1 is relevant for user 1 U1. In tenant 2, Teams channel 2 T2 is not relevant for user 2 U2. However, it can so happen that in the embedding space, T1 is close to T2 and U1 is close to U2. Can such a setting cause problems in the training of the downstream recommendation model? A study is needed to understand whether this situation impacts the training of downstream model. And if so, how much does it impact? And finally, how can we mitigate these issues during embedding learning? To conclude, in this talk, we talked about Project Digo and its goals. GNNs have shown great improvements in performance on various classification and recommendation tasks. However, we saw that significant challenges are yet to be solved to make these systems using these models practical. In case of queries regarding DIGO or the challenges presented in this talk, feel free to reach out to any of the below mentioned people. Thank you all for listening.